Next, page 412, infinite limits. Now, if you have a regular function, such as, let's say, f of x, excuse me, f of x equal to x cubed, then as x goes to infinity, obviously the function goes to infinity as well. Okay, so when that happens, we just say that as x approaches infinity, the function approaches infinity. So let's turn the page. There is actually a specific. Okay. However, what we are focusing in most of the time is not the function that goes to infinity. As I've mentioned in chapter 1, if a function goes to infinity, there's not much we can do about it. Except that we know, well, it's gone. You know, it's way out there. Infinity is not a number. Infinity is only a direction. So there's nothing we can do about it. However, what we are interested in is sometimes, I don't know what's the matter with me, but sometimes when a function goes to infinity, when x goes to infinity, the function doesn't. The function actually approaches a specific number. When that happens, then we say that the function has a limit at infinity, which equals to some number. Let's say call it L. Okay, so let's look at the definition on page 413. Which gives you a formal definition of f. Now this particular definition is very similar to the delta epsilon definition we had earlier. And it says, we say a function f has a limit at infinity if there exists a real number such that for all epsilon that's bigger than 0, there exists a large number n such that the distance between the function and L will be less than epsilon for all x that's bigger than n. Now that is, and a similar definition is for negative as x approach the other side of the infinity exists in the same way. Now that just means that as no matter how small an epsilon, that is the error that you allow, like nanometer, right? You can find a big enough number such that all x's that's bigger than that big number will land f of x within the epsilon error margin. And when that happens, that's not just one or two, it's all of them. All the x's that's bigger than some number n, some large number n. Okay, we don't care how big n is. N is some big number that for each epsilon that somebody can throw at you, you can show them the n where this relationship works. The f of x, as long as x is bigger than the n, then f of x will be less. F of x will be within epsilon of the limit. Now, to see what that means, let's let's look at example 4.22. The example 4.22 says we need to prove a very simple limit, that is limit example 4.22, where we are supposed to prove that the limit as x approach infinity of 2 plus 1 over x equals to 2. All right, now normally the way we look at this is to argue that without a formal proof, okay, if we're just calculating, then we simply argue that that as x approach infinity, 1 over x will approach 0, okay, because x is huge, and as the denominator becomes huge, the fraction itself will become nothing, and therefore this limit will be equal to 2 because this approaches 0. Now the formal proof, how do we prove it formally, is like this. Now to prove it formally, okay, we will choose an n that given epsilon that's bigger than 0, okay, so we say given epsilon that's bigger than 0, then we will we'll let n, the large number, to be equal to 1 over epsilon. The reason I do that is because this says 1 over x. So I just did the same thing. And that should come out. So therefore, we'll choose any epsilon that somebody tosses us, we'll choose a large number that's 1 over epsilon. Okay? Now when that happens, then for all for all x that's bigger than n, okay, then this particular relationship 2 plus 1 over x, that's the function, okay, f of x, and its distance from the 2, which is the L, okay, so we're doing f of x minus L here in the definition, is going to be, okay, let's calculate that. If x is bigger than n, well, first we'll do the simple subtraction, that's just 1 over x, all right, and then and as being the x is approaching positive infinity, the absolute value goes away, which equals to just 1 over x. And being the x is bigger than n, 1 over x will be less than 1 over n. Okay, that's one of the basic rules of inequality. And then which is epsilon. So here we finish our proof. That is, given epsilon bigger than 0, we can find this n defined from epsilon in terms of epsilon, such that for all of x bigger than n, the function, the distance between the f of x and L will be less than, here's less than epsilon. Okay, that is the formal proof. And that's how you prove this kind of thing. We're not going to be doing any of these proofs in homework, so please try to go home and redo this example yourself to see if you can get it to come out. That is, just look at the question, formal proof, and try to see if you can do this without looking at the stuff by following the logic. Now let's look at the next thing, which says that we have an infinite limit. Okay, if this definition works in such a way that okay, we'll read this thing out loud. It's not that big a deal, because as I've mentioned, going to infinity, there's not much to do. But we say that a function has an infinite limit at infinity. Actually, I don't ever say that. But, well, whatever, we'll go along with this. And write limit of f of x as x approach infinity equals to infinity if for all m bigger than 0, there exists an n bigger than 0 such that f of x is bigger than m if x is bigger than n. In other words, instead of f of x is distance less than epsilon, we're saying f of x, the value is going to be big. Okay, as big as you want. That's the definition of the delta epsilon the delta epsilon definition, which just simply states that for all situations where x is big, f of x is also going to be huge, and doesn't matter how big you want it. So that is that's the infinite limit. Well, why are we calling it that? It's just it goes to infinity. That's all I can say about it. So let's look at the next problem. An infinite limit at infinity. Sure, let's go through this too, because this kind of formal proof is very interesting. Even though you will not be doing it in the homework section that I noticed, I didn't see anything that asks you to do this. But it's still cute to go through the formal proof, and because that's the beginning. You can see how advanced mathematics is done. It's done with this kind of a formal definition and formal proof. So let's look at example 4.23, which says we need to prove that as limit as x approach infinity of x cubed, that equals to infinity. Now, normally when you do the homework, you're just going to say, well, And if x goes to infinity, well, obviously x cubed goes to infinity too. What do you want, right? But this, we're doing a formal proof here. So what we're going to do is we'll let's say, so given from the definition, given any large number m bigger than 0, we'll let n equals to something. Let n equals to, being that does that, we will call it the cubic root of m. Right? That is because it's the x to the power 3, we will get it such that it comes out to be identical. So cubic root. All right. So and then if x is bigger than n, then x cubed is going to be bigger than n cubed. What did I have? Okay. Okay, x bigger than n, x cubed bigger than n cubed. So far, so good. And what is n cubed? N cubed, from the relationship we designed earlier, is just this thing cubed, which is just the cubic root, and then cube, which is equal to m itself. Okay, so what do we have? So by definition, given some kind of a number, we can find another large number such that as long as x is bigger than the second large number, f of x, is bigger than the first large number. That is the definition of the infinite limit to a infinity. Therefore, the proof stands. That's the formal proof. It's very short because, yeah, and it's just a cute definition. So let me erase. Next, let's look at on page 405. Did I say 405? No, it's 415. Sorry. All right, on page 415, towards the bottom, let's consider a function's end behavior. That is, what happens when the function goes to both ends? Does it do anything? That is, does it go to infinity, which happens a lot of the times, right? Like x squared, f of x equal to x, or, well, a lot of functions go to infinity. However, sometimes a function might reach a horizontal asymptote, y equal to L, such as 1 over x. Okay, anything when you have the denominator that might be 0 at some point, then it's reaching some asymptote. No, that's the vertical asymptote, but a lot of times they are horizontal ones as well. Now, or as the function approach. So the first possibility is the function reaches some kind of a horizontal asymptote instead of taking off. The second possibility, of course, is the function took off. Okay, it went to infinity or negative infinity. And there's a third possibility, is that it doesn't go to infinity, but it doesn't stay put into a point either. It just sort of bounces around infinitely. Okay, it's always bouncing, like the sine function. Okay, it goes up and down forever, right? It doesn't approach limit or go to infinity. So that would be the first possibility, the third possibility. So now let's see. So the first thing we should consider is polynomial functions. Now for polynomial functions, that is when limit is the limit of x to the power n. N can be positive numbers such as 1, 2, 3, 500, 10,000, whatever. When any kind of a polynomial, it looks something like a parabola, except that as the degree goes higher, then the polynomial looks narrower. Okay, because as the higher the degree, the faster it grows, so it shoots straight up, and as a result, it looks narrower on your graph. So that's the polynomial, and of course for the polynomials, as x goes to infinity, the function goes to infinity, and that's of course the one. It somewhat depends on well, not a matter somewhat. It depends on whether the power of the polynomial is even or odd. Because if you have an odd polynomial, of course, then it reflects, part of it goes down. As x goes to negative infinity, the polynomial raised to an odd power will also become negative. So it sinks clear down to negative infinity. So and then if the polynomial is multiplied by some constant number, such as 5 or something, they call it c here, then it depends on the constant. It might flip if the constant is difference negative, it might flip the polynomial over, and then it might go to negative infinity instead of positive infinity, but it's going to infinity somewhere all the time, all the same anyway. Okay, so let's look at an example on the next page, example 4.24. Actually, let me just assign that as homework, because that's pretty obvious. And let's move on. Okay, next, let's consider polynomials in general. Now, polynomials, which as an example of it, we'll write a standard normal. What would you call this formula? It's a polynomial. Anyway, we'll call it this: f of x equals to a standard representation for a polynomial is f of x equal to an x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 plus a1 of x plus a0. Now that is a standard polynomial of any power n. What is it called? Degree. Any degree n. The n is the degree of the polynomial. Now, remember that when you see a polynomial like this, there are a whole ton of symbols, right? There's a, there's n all over the place, and then n even becomes minus 1, and then a1, a0, there's lots of a's and numbers, and it might look confusing. So when that happens, you just write or think about an example in your head. Okay, for example, we'll have the example, in fact, the book shows here is, let's have an example of f of x equal to 5x cubed minus 3x squared plus 0x plus 4. Now you just see some random sample polynomial in your head like this. The reason is that way, you know that 5 stands for an, okay, where n equals to 3. An is one variable. Remember that. Whereas next, an plus 1 is negative 3, and n minus 1 is 2, and then a1 is 0, because, yeah, that's how this example works. You can be 0, and then a0 is 4. So then you see the example in your head, and so that your brain doesn't get blown away when you see too many symbols at the same time. And eventually you get used to it, and then you look at it, and it doesn't mean nothing. I mean, it doesn't have any scary implication. But for now, if it makes you feel more comfortable, envision or write down any random polynomial when you see this particular representation, so that you're not confused by too many symbols at the same time. Okay, now what the point is, however, is when we have a random polynomial of n can be any degree, such as the example here, what we're going to do is do this interesting factoring. We shall factor to get, so f of x equal to, we'll factor an out and x to the power n out of it. And so then, if you factor that out of it, the first term that's left is 1, of course. You say, well, how are you going to factor that out? Because the rest of it doesn't have any of these things. Well, what we do is then we blatantly do division. That is, we'll divide by this term, so it becomes, what is this? Okay, so the we'll just divide everything with this. Okay, so so everything is being divided. So we get an minus 1 divided by an, and then xn minus 1 divided by x to the power n. In other words, it's like x squared divided by x cubed. So we have 1 over x left. Okay? You simply take this term divided by this term. So you have 1 over x. And when you multiply this together, it becomes that. So, and you continue doing that, okay? Plus, you divide it by through every single term, and then eventually you get a1 divided by an. And by the time you got to a1, the x power has gone down to, excuse me. So the x power is going all the way down to 1 over x n minus 1. Okay? And then eventually to the a0, where divided by an, and then to the power x to the power n, because every single term is being divided by the first term. Well, I'm not going to write down an example here, but you can do that in your head. Divide everything by 5x cubed in your example to see what it looks like. It will look something like this. And so, next, now what that means that now you look at this thing is if we let f calculate the limit of f as f of x goes to infinity. Okay, now if we were to calculate this and you look at this thing, it equals to what? In this particular term, 1 stays as 1, but everything else, see, x goes to infinity, so 1 over x will go to 0. So this thing will go to 0, and so will this, because this is the next power, plus dot dot dot. And plus, so this is x to the power n minus 1, and x to the power n, so that goes to infinity even faster. So everything here gets wiped out. The only thing you have left is just 1. So as the limit goes to infinity, then this limit is the same as the limit of, as x approach infinity, of just an to the x to the power n. That's it. So we multiply the first one out, because everything else get knocked out because it's going to go to 0, every one of them. Now at this point, and therefore, and what about it? So therefore, this means that the rule is that if you have a polynomial, then the infinity behavior is identical to the infinity behavior of just the first term. Okay, all the rest don't matter because they are inferior. All the rest get dominated by the first term. The first term is the only thing that matters. And this is true whether x goes to the positive or negative infinity. So we'll put the plus or minus sign in here to indicate that. Okay, it doesn't, whichever way it goes, the argument stands. The positive or negative infinity, a polynomial at the end behavior is identical to the function, to the polynomial with just the first term. Okay. All right. And as an example then, is in our example, the limit of f of x of all this stuff is the same as the limit of just the first term, fx cubed, as x approach infinity. But that's only true for infinity, of course. The rest of the function is very different, and the limits don't have anything to do with each other. Now, to show a graphics example of this, then let's look at the next page, where your book draws a nice picture of the function. You see the red one is the original function, and the blue one, whatever that color is just the function of just the first term. As you can see, while it's different in the middle, towards the end, they're coming together. Okay, so that's because the reason is because all the rest of the terms get dominated. Because once you do the division, they all got knocked into 0. All right. So next, we're going to determine the end behavior for rational functions. let's look at example 4.25 on page 418. Now, we are going to determine the limits of the function as x approach infinity and negative infinity. Now, so far, most of the stuff we did, doesn't matter which way the x approaches infinity or negative infinity, the results are the same. But that's not necessarily true. Okay, it really depends on each function. What happens to x on the two ends? They're not directly related necessarily. They can approach very different things. So let's look at example 4.25 part A, where it says f of x equal to 3x minus 1 over 2x plus 5. Okay, that's some simple rational function. And you notice that the degree of the x's are the same top and bottom. The degree means the power here. The power is 1 here and 1 here for both x's on top and bottom. And that matters in determining the who's dominating. That is, if there are a lot of degrees on top, it will go to infinity. If there's not enough degrees, then the bottom will dominate. That kind of thing. But we'll look at the details. Okay, let's turn to the next page. Okay, so how are we gonna calculate the the limit as x approach to some infinity? We are going to calculate it by pulling this trick that we just did earlier. That is dividing the x out. So we are going to the limit as f of x approach infinity. Okay, we'll do a positive infinity first, and we'll be equal to, we'll do this division, same limit. Okay, we are gonna divide everything top and bottom by x, so we get 3 minus 1 over x, and then 2 plus 5 over x. Normally we do it the other way, right? We simplify a rational function. But in this case, we're going to go backwards and divide stuff so that you have a bunch of small fractions here. And why are we doing this? Because as x approach infinity, these terms get knocked out. And all you got is the numbers left. And therefore, you have this equal to the limit of as x approach infinity of 3 over 2, which is just 3 over 2. That's it. And that's the limit of this thing. That is, the function as x approach positive infinity equals to 3 over 2. Now, you notice that even if x were to approach negative infinity, what we just said still works. This will get knocked out into 0. As a result, this proof applies to negative infinity as well. So it works for both positive and negative infinity. Plus, minus. All right. So, and the answer for both cases is 3/2. You just divide the x's out and make it go to 0, and that's that. And the graph of this is, if you were to graph it, you see something like this. Okay, see the horizontal asymptote, which is 3/2. Okay, the x is approaching 3/2 on the right side. On the positive x is approaching from the bottom, and then on the left side is falling down from the top. Either way, it's approaching it. So that's our first example. Let's look at the next example, part B. Part B says, okay, first let's write down the problem. Part B says f of x is a more complicated rational function. F of x equals to 3x squared plus 2x, and then over 4x cubed minus 5x plus 7. All right, so we have all this. Now this, first thing you look at this kind of problem is look at the highest power. What is the highest power? Now notice that the bottom power is higher than the top. And that's going to mean something. So where does the limit go? Well, the limit when that happens is we're going to divide everything out, and we're going to divide it by the highest power. Okay, so following the same trick as we did earlier, the limit of f as x approach positive infinity. We'll do the positive first and then think about the negative later. All right, so it's the limit of fx, and we're going to divide this thing. We'll divide it by the highest power there is. So we have, so the fraction turns into 3 over x. There's one x left here, plus 2 over x squared, because we're dividing by x cubed. Oops. We'll divide everything by x cubed, that thing, x squared. So, and then this just has 4 left. 4. Excuse me, my marker. Okay, 4 left, just 4. And then that is going to be equal to 5 over x squared. Okay, we're dividing by x cubed plus 7 over x cubed, right? And that should be correct. So what do we have here? Well, we had, then at this point, we allow x to go to infinity, and x goes to infinity, these things become 0. These things also become 0. The 4 stays, but there's 0 on top. So then we get, I've got to write down the limit. Okay, that equals to 0. Because, yeah, well, the numerator becomes 0. So you can see that anytime you have a rational function where the top power is less than the bottom power, then everything just dies. Okay, it just get knocked out. Because you're dividing by the highest power, and the bottom stays alive, right? Still has a number, whereas the top all goes to 0, so everything automatically goes to 0. And that is also true if the x is negative infinity, goes to negative infinity. The same story applies. So this answer applies for both infinities. And that's the answer of part B. See, nice and neat. Okay, so what does f look like? Well, if you are to plot it out, or just look at your book, see, and f looks something like this. As you can see, it does various stuff in the middle. Specifically, it has a vertical asymptote, which we'll worry about that later. Well, vertical asymptote is just at the point where the bottom is 0. That is the quadratic equation. Is there a quadratic equation? No, the cubic equation on the bottom has one root. Okay, if it goes to 0 there, then the function will break up into a vertical asymptote. But right now we're looking at the end, and both ends go to 0. Although one approach from the top, and the other one approach from the bottom, but the idea is the same. All right. So next, let's look at problem number C. Okay. Now, problem number C, here it is. Go back to seeing what is problem number C. I'll write it down here. Problem number C says f of x, okay, equals to 3x squared plus 4x over x plus 2. So problem number C has a different case. See, you have the same power here, right? You have higher power on the bottom. Now problem C has a higher power on top. Now let's see how that works out, right? Then for problem number C, okay, let me find it. Next page. We are going to divide everything by the denominator only. So why? Because we can't allow the denominator to go to 0. Okay, so we're only going to divide by the power of the denominator, which is also applied here and here. So let's do this. The power to divide by the x, so we can only divide by everything by x. So the limit of the function f as x approach positive infinity, we work on the positive first, f of x equals to dividing by only the highest power in the denominator. We have, so this the top becomes so this becomes 1 plus 2 over x, and the top becomes 3x plus 4. Okay, that's pretty good. All right, so now what? So we get this situation where the bottom, as you allow x to go to positive infinity, the bottom becomes 1, okay, because this get knocked out, but the top is going to go to infinity because it says 3x. X is infinity. The top, when the x approach infinity, so does this, right? And therefore, the limit of this thing is as x is going to be infinity. The limit as x is infinity. Okay, so while the earlier examples approach some kind of a specific value, including 0 or some number, when the top dominates, then the function will approach infinity. And then we then look at what happens when x goes to the negative. The limit as x approach negative infinity is different this time. Negative. Anyway, so as x approach negative infinity, f of x is, when x is negative infinity, the bottom is still just 1, and that's becoming very, very negative, and then so that approaches negative infinity. Like negative a million or something, that becomes negative 3 million, etc. It becomes negative infinity. So that is, so as x approach the negative infinity, the function takes a dive to the bottom side. All right, and to look at the graph, then we see something. See the graph that one side takes off and the other side dips down and dips out of sight. Okay, so that is what happens at infinity. Now, there is one thing that we need to look at. This before, let's see. Yeah, but now we're done with this problem because all we need to know is what happens when x approach infinity or negative infinity. However, there is another point that might be interesting to consider. That is, this function f of x. You can represent it as, it has an unusual characteristic. That is, when you look at what's happening here, all right? Now, when you look at the graph of the function, it looks like this, right? I mean, you look, and the sides looks almost straight. The reason is because it's approaching some kind of a slanted asymptote. That is, to be exact, it looks like this. Yeah. Well, they draw it a little differently. See the red line? That's called an oblique asymptote because the function is approaching the line called y equal to 3x minus 2, which is and how are we gonna calculate? Now, to show that, let's look at that more carefully. Okay. First, we can break down this function f of x. F of x equals to this function right here. You can do something called the long division, which then may make you equal to, it'll come out to be 3x minus 2, which is the whole part, and then some kind of a fraction, remainder, which is 4 over x plus 2. Yeah, I'm not going to do the fractional division here, but that is taught in algebra or something, maybe later. If you don't remember how to do it, it's easy to forget. Okay, just look up how to do long division of polynomials. It's really straightforward. It's similar to regular long division of numbers. If you don't remember how to do that either, look that up too. But for the most part, look up how to do the long division, and then and if you do the long division, which is a standard process, you will come up with something like this. And what about it? And here's the interesting point. Okay, because if you take the limit, if you subtract the two functions. So let's do this. The limit of as x approach infinity, of the function f of x, that's that thing, okay, that one. If we do this subtracted by just this part of the function 3x minus 2, what happens when you subtract it? Parentheses, okay? The limit, that is, well, I want to calculate the limit of the difference of these two functions, the original function and just the difference between the original function and just that part of it, the part that isn't in the fraction. So to calculate that, then we do the subtraction. That would be equal to the limit as x approach infinity of just 4 over x plus 2, right? Because I took this thing and subtracted 3x minus 2 out. So we just have the fractional part left. Now that, as x approach infinity, that equal to 0. You know, x become huge, it is 0. So that equal to 0. And you know what that means? It means this function behaves identical to this function when x approach infinity. Okay, the difference of them will become negligent. Now the same thing can be said if it's for negative infinity as well, because for negative infinity, this, as x goes to negative infinity, this still approach 0. So this line applies for positive or negative infinity. And as a result, what that means is that this line, this thing right here, which is called y equal to 3x minus 2, is called an oblique asymptote. The oblique asymptote is obtained by doing long division, okay? And then you come up with some line. Well, only if this end up being a line. Sometimes you might have x squared, then is not a thing. I mean, it's something else. But being that it end up being a line, okay, this line is called the oblique asymptote, and it looks like this, like the one you see earlier. See the line here, which is red in your book, and you see the function approaching it on both ends. All right, so that just means the function's end behavior approaches, it goes to infinity, but it does it in such a way that is identical to some line, okay, 3x minus 2. All right, so here's the conclusion at the bottom of what we just said, that the first, if for any kind of rational function, you have similar to, say, that or that, okay, you have a polynomial on top and polynomial on the bottom. All right, now if the degree of the numerator is the same as the degree of the denominator, then you have a horizontal asymptote that's equal to the fraction here. That's rule number 1. That is the fraction of the first coefficients. Like in this case, the asymptote is 3 over 2. See, y equals 3 over 2 is the asymptote. Now, if the degree is less, as in this case, the degree on top is less than the degree on the bottom, then an asymptote is simply the y equal to 0. Okay, everything just collapsed on both sides. Now, if the degree is greater, then stuff goes to infinity, right? Like this case, when the degree on top is greater than the degree on the bottom, then stuff goes to infinity. However, you can do some long division, where if you end up with a degree that's only one more on top is one more than the degree on the bottom, then you end up with a result like this, which is just a division where the result is 1 to the degree 1, which is a line, and that line is called the oblique asymptote.